pressure. Okay? Lots and lots and lots of different units of pressure. Biggest deal to remember, 1 atmosphere. 1 atmosphere is our big standard. That's really what I want you to get out of it. If you have to move into future chemistry classes, they might make you do a bunch of unit conversions. We won't worry about those unit conversions this semester, but you could do them. Okay? Which gets us to kind of the big crux, I think, of this section. Thinking about things that would affect pressure. Okay? So the first thing I want to come up with is I don't want to write pressure a whole bunch of times. I want to come up with a 1-letter code. P. Luckily enough, that one's available. So there we go, P. What would affect the pressure?
The heat volume.
Okay, temperature will affect pressure. Okay, how will it affect the pressure? As we add energy in, as we increase the temperature, what happens to the pressure? It increases. Okay, so we see a direct relationship between those. Okay, that relationship we can show with, it's not an alpha, but it's an equality thing. Okay, ultimately, all this is really saying is that if we increase temperature, we increase pressure. Okay, and we see that as a nice direct relationship. Okay, what else affects pressure? Volume. How does volume affect the pressure? If we increase the volume, so we take a look at a container, here's a little container, here's our particles. Each of those particles pushes on the outside of the container. If I now move to a larger container, what happens to the amount of times those same particles hits the sides of the container?
Goes down.
It goes down. Less impacts means?
Less pressure.
Less pressure. Okay? Which means, if we look at our proportionality, these are inversely related. Okay. The bigger the volume, the smaller the pressure. So 1 over a large number is now a small number. Okay. Increase volume, decrease pressure. What else could affect it? I know where you're going with elevation. The problem with elevation is you're now referencing an open system, and that's going to be too hard to mimic. We're thinking about closed systems. How about the number of particles? Okay, so if I take a look at that same container, what happens with that same container if now I put in more particles? What's going to happen to the pressure?
It increases.
It's also going to go up. Okay, so that is directly proportional. What unit or what symbol am I going to use for the number of those particles? N for number of particles. Because this is a chemistry class, are we going to be able to count the number of particles? No, that's going to be too difficult to count out the individual particles. So could we count out, say, a large number of those particles? Like a mole. And so what this N is now going to represent is our moles. Okay? When we increase the number of particles, we will increase the pressure. Okay? Do I have to relate just pressure to moles, or could I relate moles to volume? Or moles to temperature? Okay? Because pressure is something in common with all of them. Yes, all of them can come related to each other. Okay? These observations were things that were made a long time ago, and because they were made or had some initial discoverer, they got to stamp their name on it. So that relationship between volume and pressure, I think it's Charles Boyle. No, I think I'm screwing it up. Somebody Boyle, okay, got to attach his name to that relationship, saying that volume and pressure are directly related. Temperature of the gas can affect it. When we look at temperature and pressure, that's Gay-Lussac. Okay? If we look at volume and temperature, that relationship, that came from Charles. Okay? Number of particles related to the gas in the container. Okay? We see that with pressure, and we can see that with volume. So all of these relationships are in there. And so ultimately what happened is that somebody took all of this random kind of data that was collected out there and said, well, these are all kind of directly related to each other. I can push them all together, and if I put them all together into one thing, I can discover this magic constant. Right? If I organize the pressure of any gas, its volume, the number of particles, and the temperature, and I put them into a solve, pressure times volume over moles times temperature, it doesn't matter what the gas is, the pressure, temperature, moles, all of that, okay? For any given system that has those things, it will come out to be a constant. That's kind of neat. Okay? And so because of that, I can now make comparisons to different states and different systems, okay, through this expression. That R value comes in at 0.0821 atmospheres times liters per mole times Kelvin. What was atmospheres a measure of? Pressure. What is liters a measure of? Volume. Moles was a measure of? The number of particles. K is Kelvin, temperature. PV and T. There's our expression. Okay? That's a fraction. Most people have a hard time with a fraction, so typically what happens is that this fraction gets rearranged to come into the expression PV equals nRT. And you'll hear chemists reference Pivnert. Okay? Pivnert is a powerful equation because it ties a lot of different measurable quantities together and allows me to see those relationships pan out. So that's pretty cool. Right? With this, I can go through and solve for a pressure if I know those three other symbols or those three other measurables. I could solve for the volume if I knew the other three. Right? So this is kind of neat. Right? If I have those measurable things, I can determine one of the unknowns. That's fun. Okay? On top of that, because I know these are all equal to a constant, I could go through and change the conditions. I can start at conditions A and make conditions B for that same gas. Okay? In that change, I know that it's still going to equal to R. Okay? So what that means I can do is now say the pressure of A times the volume of A equals the pressure of B times the volume of B over the moles of B, temperature of B. All of those relationships that we attached names to, Charles and Boyle and Avogadro and all those fun things, are hidden in here. Okay? For instance, the relationship between pressure and volume. Okay? How is that hidden in here? Well, if we look at the pressure and volume situation, what are we saying is happening to the number of particles in the temperature? They're staying the same. So that means Na equals Nb. So what happens? They cancel out. Okay? I can then potentially rearrange these things. Say the pressure of A equals the pressure at B times the volume of B over the volume of A. I can see those relationships kind of fall out of that expression. And that's pretty neat. Okay? With that, I could go through and solve something like this. The volume of a container is doubled. Assuming the temperature and moles are not changed, what happens to the pressure? Okay. Have I specified really any numbers? Not really. For those of you saying, well, yeah, you did. I did kinda. What number did I specify?
2.
Doubled. The volume of my container and secondary conditions is twice the volume that it started at. Right? That's what that question says. The question is also now asking what happens to the pressure. So I want to know what PB is. Can I figure that out? Right, yeah, there's a variety of ways to figure it out. What might you say right off the bat? The pressure should decrease. How do you know that?
Effect
we'd established that volume and pressure aren't indirectly related to it or inversely related to each other. So if we increase the volume, the pressure must decrease. How much is it going to decrease by?
Double.
It's going to decrease by doubling?
Well,
By a half. Okay, it's going to half. So you've reasoned through that. For those of you that aren't able to reason through that, that's okay. That's why we have these expressions that we can deal with. Okay? What is Na equal to? The number of particles for A is what? Nb. What is temperature A? Temperature B. So when we go through and look at our expression all the way up here, what happens? Na I know is Nb. Tb I know is Ta. What did I say Vb was? 2 times Va. The NAs can cancel, the TAs can cancel. The expression that I'll end up with, PAVA equals PB 2 times VA. What did I want to solve for? PB, so what do I got to do? Divide both sides by 2VA. What happens? The VAs cancel. The result for my pressure is 1/2 PA. What did you guys say happened to the pressure? It halved. There it is. The mathematics support our kind of logical representation. For those of you being like, well, damn, do I have to do all the mathematics? No, you don't. If you got it in your head, that's cool. That's all I really need. Okay, this is one of those chapters where I'll accept you just kind of reasoning your way through it. Okay? With this neat equation, though, we should now be able to do some calculations. So we could start plugging pressures, volumes, moles, R, and temperature into this. Okay? Because I have a hard time remembering R, I'm going to backtrack here, because I'm going to need that number here in a second. Okay, 0.0821. Okay, I got to remember that, 0.0821. Okay, because we now have an equation, what could we potentially do with an equation? We could solve for some stuff. So, how many moles of neon gas occupy 2.34 liters at STP? Okay? So I want you to go through and attempt to solve this, and I want you to do it as fast as possible. I am also going to attempt to do this, and we're going to see who wins. Those of you laughing, you should be able to beat me. And you probably don't want to pay attention to what I'm writing. You copying what I'm writing? Anybody finish it? Okay. Just saying, you probably should have. Apologize for the dead silence in the recording. Steal a calculator? No, you don't have a calculator. Damn it. Yo. Just for the record, I have to open the calculator and borrow a calculator while you all are still trying to get this answer. Have you guys got it solved yet? Yeah, okay. No, I'm just going to set that. Okay. How many people solved it that way? How many people solved it a different way? How'd you solve it? How many people solved it, period? Okay, we got a few hands. Okay, how'd you solve it?
I used the conversion for gas at standard.
You mean what you used was the process that we've been talking about the entire freaking semester? Interesting. So those people that did not solve it, did you attempt to solve it the way we've been talking about doing it the entire semester? Mm-hmm. Okay, just checking. What are we ending with?
The thing is like 0.1.
What are we solving for? Sorry.
Moles of neon gas.
Moles of neon gas. What do we start with? Are liters of neon gas the same thing as moles of neon gas? No. So what do I need to do? What do I want? Moles of neon. What do I need to get rid of? Liters of neon. Is there a conversion factor that does that? Yeah, what was that conversion factor? 1 mole is 22.4 liters. For those of you that struggled, where did you struggle with that calculation?
Remembering the conversion.
Okay. To know to bring in that 1 mole is 22.4 liters. Did I tell you you needed to memorize that?
Yeah.
Just checking. You should memorize that. Because if you don't memorize it, guess what you got to do? PV equals nRT, down at the bottom. So PV equals nRT, what happens? Okay, we're solving for moles, so I rearranged the equation. N was our number of moles, equals PV over RT. Pressure, STP, standard pressure is 1 atmosphere. The volume, 2.34 liters. R was 0.0821 atmospheres times liters per mole times Kelvin. Our temperature, standard temperature, 273 Kelvin. If we take a look at our units, atmospheres cancels, liters cancels, Kelvins cancel. And I would end with a unit 1 over moles. Everybody see that? What is the unit 1 over moles? It's just moles. A lot of people tend to have a problem with that. Does anybody have a problem with that? You're like, no way, that's crap. That can't possibly be true. Okay, fine, that's what I said. 1 over 2 equals 2. Really, 1 divided by 0.5 can't possibly be 2. Yeah, no, my calculator tells me that. This is 1 over 1 times 2 over 1. Play some little algebra games, and there it is. 2, the same thing's happening with our units. 1 over moles is the same thing as 1 over 1 times the inverse of our denominator, moles over 1. We end up with moles. We get 1 over 0.0821 times 273. I don't know why I had to rewrite it up there. That was kind of dumb. But I entered into the calculator, and interesting enough, I just split it. It's kind of weird, right, to split it like that? That's silly. Why would you split it like that? Here's why. If I take 1 over 0.0821 times 273, 0.0821 times 273 is what? 22.4. What did you guys do in the calculation in black? 22.4 where? In the denominator. Where did I end up with it? In the denominator. Where did I put the 2.34? Where did you put it in black? In the numerator. Guess where that conversion factor, 1 mole is 22.4 liters, comes from? The ideal gas law. Okay? That relationship, 1 mole is 22.4 liters, is phenomenal at STP. What if you're not at STP? Well, that conversion factor doesn't exist anymore. What would you have to do?
Pipper.
PV equals nRT. Right? Is the mathematics process identical? Yeah. PivNert is a much more powerful tool that would actually allow you to solve multiple expressions with gases that, again, you don't work with. Right? As opposed to memorizing the expression 1 mole is 22.4 liters. Make sense? Right? So all I'm trying to draw attention to here is that that thing that we're making you memorize, number one, I'm making you memorize it. You need to memorize it. Yes? Cool. Otherwise, if you don't have it memorized, I will come back after the test and I will be like, you need to prove to me PivNert. Otherwise, I'm going to take away 20 points from your exam score. That'd suck. That's good. I was trying to be. Yeah, just kidding. I wouldn't do that. Okay? So remember that expression because it's one that shows up. PivNert, if you move into Gen Chem, you'll see it show up. If you move into engineering, PivNert's all over the place. Right? When dealing with gases. Right? If you don't have to worry about any of those things, then memorize that number, 1 mole is 22.4 liters, and just be happy. That's all you got to do. Questions? Okay. Yep.
So from doing it that way and the shorter way that you're supposed to memorize that piece, what does the final answer come up to be, just for the sake of notes?
2.34 divided by 22.4.
0.10.
Okay, I'm just checking because I got
0.1 what?
0.04.
0.04. Do I get a second?
0.10.
Okay. There you go.
0.105 if you like round it.
If you do with rounding, okay.
Oh.
I can accept that too. 0.105. Now you're saying something else? Okay. We good? So what are you going to do?
Memorize it.
Okay, thank you. And thank you for your extra emphasis, because you were extra emphasis in that you didn't do it earlier too. So I appreciate it now. Okay? So, when we deal with gases, what you are forced to memorize is that 22.4 liters is 1 mole. It comes from PivNert. That's why it's there. Okay? So, what do I want from Chapter 10? Well, the very first thing on that list is, yeah, there we go. Look at that. 22.4 liters is 1 mole. Have I said it enough yet? Have you memorized it?
Yep.
Okay, just checking. Ideally, you should recognize the utility of PivNert, PV equals nRT, because that establishes a lot of those internal relationships, and it's all done in one simple little equation. Okay? If you decide to not do that, then you do need to deal with the individual relationships between all of the individual units, like the relationship between volume and temperature, pressure and volume, pressure and moles, pressure and temperature.
What was the one between volume and temperature?
What was the one between volume and temperature? You tell me. Look at PivNert. What happens if that temperature gets bigger? What's going to happen to the volume?
It would.
And we're making the assumption that the rest of the things stay constant. If temperature gets bigger, what has to happen to volume? It also has to get bigger. Otherwise, that's not an equality. Right? That's the power of using PivNert. You don't have to memorize each of the individual ones. It's right there. You just interpret straight out of it. Okay? Let's pick a harder one then. What's the relationship between moles and temperature? They're on the same side of the equation, so that can be a little bit trickier to deal with. So what should we do?
Divide it out.
Get one to the other side. PV equals nRT. Again, with the writing it out the same. PV over N equals RT. If our pressure and our volume stay constant, if the temperature goes up, my temperature gets bigger, what has to happen to the moles?
Smaller.
It has to get smaller so that it still maintains the equality. We now have that relationship. Make sense? Cool. Almost all of gases. Dalton's law of partial pressure, just kind of a random little thing. Because of ideal gas law, the pressure exerted by each gas is the partial pressure. It's the pressure from that individual substance. If I want to know the total pressure in the system, all I have to do, I add together the pressure of all the individual particles. That's it. Because none of the particles are technically different from each other, they're all ideal, none of them have a volume, none of them are attracted to each other, I could care less what the identity of any one of them is. But if I know each of the partial pressures, I can add them up and I get the total pressure. Make sense? So how would you do it? That dead time is reading time, for the record. How would you do it? Theory, you've read it now. Some people are actually looking at me, so you've probably read it.
You guys should add them all together.
You just add all the numbers together. Really? It is that simple. You just add the numbers up. That's all you got to do. Okay? If it's not an ideal gas, then you can't do that. But it is an ideal gas. Why?
You said it was.
I'll accept that. We said it was. Do you want it to be an ideal gas?
Yeah.
Yeah, it makes life easier. So, yeah, let's stick with that. Notice what gases did I pick? All the noble gases. Why would I pick the noble gases? Those are going to be the most ideal of all gases because
They're the most stable.
the noble gases don't react with each other. Oxygen might be a horrible gas to pick because oxygen reacts with everything. Right? So we can reason through some of that. That was a good job on your part. I like it. Okay? Because of gases, that's also where we get the concept of absolute zero coming into this. Okay? If we don't have an absolute zero, then things get really wonky with Pivnert. What happens if you have a negative temperature? You'd have a negative pressure. Not a change in pressure being negative, a negative pressure. So not a comparison, an absolute, less than no force.
Inverse force?
That's a little weird. So we could try volume. You have less than no volume. Anybody, how do you have less than no volume? Exactly right. That's why we don't drop that low. Okay? That's our absolute zero, because we can't go lower than that because then those systems fall apart. That's technically our ideal gas law, and all sorts of stuff goes crazy when we make it a real gas. But we can use Pivnert to help us see that we can achieve an absolute zero. Okay? That there isn't anything lower than that. And if we hit zero, what would that mean for the moles?
Nothing.
No particles. What would that mean for volume? No volume. Pressure. No pressure. Okay? That equation starts to lose all kind of logical sense for how we deal with the world. Okay? That's really all that's coming out of it, is absolute zero is now that 0 point. We don't get negative values. We're stuck there. Okay? So everything's greater than that. Cool? Cool. Okay? So now we get some fun stuff. But before we get into the really fun stuff, okay, let's talk about sandwiches. Okay? Basic recipe for a cheese sandwich. I take a slice of cheese, 2 slices of bread, and I make one sandwich. Okay? We don't need to have a philosophical argument about the construction of sandwiches. Just accept that that is our sandwich recipe.
It's a grilled cheese.
You're missing the butter. Okay? And you're missing still a lot of stuff. Okay? So we're keeping it simple. Don't be making grilled cheese sandwiches in the microwave. That defeats the purpose. Okay? If you have 5 slices of cheese and 8 slices of bread, how many sandwiches can you make? Follow my recipe. And I would still argue it's got problems. Okay, how'd you come up with that? Okay. So what you went through and did in your head is that you said, I'm trying to make sandwiches. God, I wish there was a shorthand because sandwiches is an awful lot to write. Okay, and I was given 5 slices of cheese. Oh, Jiminy.
SC.
Just said one cheese, so it would be like one block.
One cheese.
Okay, what is the relationship between my slices of cheese and my sandwiches?
One cheese.
1 cheese is 1 sandwich, and I make 5 sandwiches. You all said there were 4. I just got 5.
You also consider the relationship to bread.
Slices of bread. Slices of bread to sandwiches. 2 bread, 1 sandwich, and I get 4 sandwiches. And I get a bunch of people laughing, going, this is silly, this is stupid. Okay, what idiot would screw this up? Okay. So let's just do it.
Okay, bread and cheese.
Your turn.
Do we have to balance that?
Yep.
Put it together. You got the same process. You've proved your awesomeness. Mouth where your pen is. Not laughing so hard now, are you? Okay. When we went through and solved our cheese and bread and stuff sandwich thing, okay, we went through and set up 2 separate conversions. Okay? We took our 5 slices of cheese, we took our 8 slices of bread, and we ran those independent of each other to determine how many sandwiches. When we run that top question or that top conversion to get slices of cheese into our sandwich, did you evaluate the slices of bread? No. It was irrelevant to our question. Why? There's too many pieces. So what do? We picked what we wanted and what we started with, and we ignored everything else. We just said, there's enough. Okay? Then what did we do when we went to the slices of bread? Did you evaluate the slices of cheese? No. When did you evaluate slices of bread relative to slices of cheese? When you got to the answer, and you said, which of those produced the fewest amount of sandwiches? Okay? That's when you made that comparison. So when we go through and do a limiting reactant calculation, what you're going to have to do is convert your starting materials into products. Sandwich pieces into sandwiches for each of the starting materials, just like we did with our sandwich. Okay? Why does this question now all of a sudden become way different? There's 3 pieces now and 1 sandwich. So now we added mustard, and all of a sudden you're losing your minds? Okay? Or pickles. Okay? Pickle. You can't make a face at pickles. Pickles are awesome.
Pickle and cheese sandwich.
If we're going to get into that argument, my favorite, slice of cheese, mustard, pickles. And then if I'm feeling adventurous, another slice of cheese. Phenomenal. You should try it. Yeah, I said cheese. So when we go through and solve this question, we're doing the same process. Okay? What is our sandwich? We're being asked to solve for our sodium hydrogen carbonate. Okay, and in particular, what unit of them? Moles. Given what to start with?
2 moles of sodium carbonate.
Moles of sodium carbonate. How do I convert moles of sodium carbonate into moles of sodium hydrogen carbonate?
Using the balanced chemical equation.
Balanced chemical equation. Which was balanced. And from that balanced chemical equation, we know 2 mole sodium hydrogen carbonate, 1 mole of sodium carbonate from the coefficients from our equation. we were also trying to see if maybe the cheese was our limiting reagent. So we go through and said, well, I had 2 moles of water. What happens? Moles of water, I need to cancel out. What do I want to bring in? The moles of sodium hydrogen carbonate. That relationship was 2 to 1. Okay. Then I also go through and I do it. 1 mole of CO2. Bless you. Yeah? Now we can compare 2, 4, and 4. So how much sodium hydrogen carbonate can I make? 2. Once I hit that 2 mark, I've now run out of CO2. If I don't have any more CO2, I can't make any more sandwiches. No mustard, crap sandwich. No judgments. Okay? Does anybody see anything in there that are like, but couldn't you just done this? What do you have? You see something, you got a suspicion, but you don't know? Because there's a couple other people that shouted something out that I think want to say something. What did you see? Which one step? Which one of these steps should you do? The last one. Why did you do just the last one? What's that? Okay. So, and this is where we're kind of getting to. Can we just shorten the amount of steps? Why are you picking the last one? Because it has the smallest number. Okay. And in this case, that happened to match the answer. Do we know this 2 is smaller than that 4 if we never did the 4? Okay. So let's try that again. Do you know that 2 is smaller than the other numbers? You said yes because you multiply it. You multiplied what?
1 mole of CO2. You did the equation, I guess.
What equation? This equation?
Yes.
Okay. But couldn't I have multiplied 0.5 by 2 and gotten 1? That's a smaller number. Okay. So I think where you're trying to go is what Savannah is suggesting. You want to try and suggest it again?
Just look at the question. It says 1 mole carbon dioxide.
So you're looking and saying 1 mole of carbon dioxide is smaller than 2 moles of water, which is smaller than 2 moles of sodium hydrogen or sodium carbonate. Is that what you're saying? Yeah. Yes. So you're saying the smallest number that we're starting with works as our final answer. Guess when it works. This case. In fact, it rarely works. And in fact, on an exam, what you should do, if you're short on time, pick the largest mole value and run that calculation. Because what is a student going to instantly reflex to? The smallest number must be the answer, which turns out to not necessarily true. And because as a test writer, I'm trying to see if students actually know what's going on, I'm going to try and flip that on its head so that students don't accidentally guess the right answer. So let me pause here. Suggested that we pick the least amount was because the least amount appeared to come in at the lowest answer here. And so that's why she said pick the least amount. Because that doesn't always work on a test, I'm not going to have the answer be the least amount. Because what's going to happen? You're going to be like, oh, all I got to do is pick the least amount. Now you get the answer wrong.
So then how do you know that?
How would you know?
If you do the equation.
I'm looking at it right now. Why do you pick the least amount?
You don't. Why do you pick this least amount at the end? Okay, that's a different answer. Sorry, I thought you were talking about over here. Why do you pick the least amount here? What happens when we achieve 2 moles of sodium hydrogen carbonate?
It's done.
We are now out of carbon dioxide. There's literally no more carbon. If you've run out of carbon dioxide, can I make more sodium hydrogen carbonate? No, you've run out of the pieces. That's why you would pick the least amount there. Does that make sense? Sorry, I was totally answering a different question. Okay, make sense? Okay. Let's try this one. Do this one. Yeah. If I did this one right, I think this is going to directly address Savannah's attempted trick. I'm totally calling you out for your attempted trick. Sorry. So if we follow her suggestion, what's our answer? We should only do the moles of oxygen, right?
Yeah.
Okay.
Is it asking for moles of water?
Good point. Horribly written question because I wrote it too fast. How many moles of water would be produced? Okay. So here we're trying to do this very, very fast. We're trying to keep it simple. Moles of water. Okay. So I've heard a couple answers shouted out already, which is going to be problematic. We heard 1 mole of water and we heard 2 moles of water. Okay, as possible answers. So this is cool. Some people are starting to crank through this in their head. Stop it. Okay. Write down your work. Attempt to solve. Just like with our sandwiches and cheese slices, you got 2 problems that you need to go through and solve. So set it up, see what you come up with. Meaning. So, right out of the gate, I'm going to point out 2 things. First answer shouted out was 1 mole of water. This is why we show our work. Okay. Next answer was 2 moles of water. Okay. If I go through and do this 1 times 1, though, and that gets 1. Right? Right at the bottom. Moles of water, oxygen. Oh, just because it's a short, fast question doesn't mean I gave you everything. We got to balance the equation first. The equation wasn't balanced. When we go back and balance the equation, what do we find?
2H2.
So 2 moles of H2O. That was one of the guesses. There it is. Spot on. Must be right. And remember, Mike said, don't do that. Go back and check all your work. When we go back and check, we take a look at the 1.5 moles, but that's a bigger number. That can't possibly be right. Moles of H2, what's the number? Coefficients? 2 and 2. What happens? 1.5 moles of H2O. 1.5 comes in to be our answer. Okay? Yes?
On the bottom one, why do you put 1 mole of oxygen instead of 1.5 moles of hydrogen?
Okay, on the bottom one, why did I write 1 mole of oxygen? To cancel. Why did I not write moles of hydrogen?
Oh, okay.
Because it doesn't cancel.
Okay, just to reiterate, so I know that I understand this. When you start with the smaller one, it's because that's the smallest amount of product that we have for this equation, right? The 1 mole of O2.
So when we look at those numbers, so what this question was here for was the suggestion was that we just look at our answer here and we say, whichever one's the smaller number, that must be the one that's going to get me my answer.
No, yeah, so I'm just double checking. So I'm just double checking to make sure. So it says that with 1 mole of O2, you could possibly make 2 moles of H2O.
You would make 2 moles of water, yes.
However, because you can have less than 2 moles, so it's kind of like the 2 is the limit, but since
2 is the maximum you'd be able to make using oxygen,
but
yes.
since the 1.5 moles of H2 comes underneath that, that would be the right answer.
Not because the 1.5 moles of H2 comes under that. What's the correct explanation?
Using H2, you don't need
Can I, so there we go. Can I compare 1.5 moles of H2 to 2 moles of water? No, why not? The units aren't the same. Once the 1.5 moles of H2 has been converted into moles of water, now I can make a comparison.
That was the comparison I was asking about.
Yep.
1. So
Now you can make that comparison.
because the 1.5 moles of H2 turned into 1.5 moles of H2O, and that came underneath the maximum number.
Yes.
That the least amount came in.
Yes.
That's fine. Okay.
Yes.
Okay.
Okay. So let's bring in some extra kind of vocab with this because the vocabulary wasn't confusing enough as it is. In this question, what was the limiting reagent? Okay. The H2 was our limiting reagent. Okay, why? Come on, screen. The most I could make was the 1.5 moles of H2O. Okay, so this was my yield. We'll call that yield. The thing that produced that amount is now my limiting reagent. So H2 is my limiting reagent. Yes? Okay. What was my reagent in excess? That's now the O2. Why do we bring in extra terms? I don't know, because life's confusing. Okay. When we go through and solve a limiting reactant problem, you do not have to always go into the product. But we do have to go into a unit that allows me to make a fair comparison. Okay, so whatever that unit is, it has to be the same for my comparison. So I can't compare 1.5 moles of hydrogen to 1 mole of oxygen because different substances. I would have to get one of them into the same unit system. In this question, I went through and got them both into moles of water. Is there a circumstance where I don't have to do two calculations?
Yeah. You could take one of the givens, so either 1 or 1.5. So if you took 1.5 moles of hydrogen, just do the unit conversion for 2 moles of hydrogen under 1 mole of oxygen. And if you realize that that's overall give you less moles of oxygen, you can say that'd be limiting.
Okay, so for those of you who didn't process all that, what happened is he explained the entire process, and he was spot on with that. The biggest part of that conversation was the end. Okay, the very last part. He said that was your limiting reagent. What he keyed in on was a different question. If I ask you how much water to make, this is your best method. Because the end result of this calculation is what? Moles of water. What am I solving for? Moles of water. If the question now changes to which is my limiting reagent, do I need to know the moles of water? No. That now changes my focus, and I can take a different tack to that. Come on, I hate it when that skips. Okay, so let's walk through what he was saying. He said, okay, what we'll do is take the 1.5 moles of hydrogen, and he said we'll do the moles, and I don't know if you said, did you start with hydrogen or did you do oxygen?
I started with hydrogen.
Okay. 2 moles, and then he went into moles of oxygen. Okay, the moles of oxygen is 1. Why is it 1? I don't accept it was in the question. It's in the balanced chemical equation. Okay, it's not the 1 from the equation. Okay, when we go through and solve that, what do we get? 0.75 moles of oxygen. What does that mean? To react all of the hydrogen, how much oxygen do I need? 0.75 moles of oxygen. How much oxygen do I actually have? 1 mole of oxygen, which means I have more oxygen than what I need, which means the oxygen is in excess and the hydrogen's the limiting reagent. So if the question is changed, I don't have to solve out for the product. Why would I solve out for the product? What's the question? How much product? Okay?
So if they were asking how much excess oxygen you had, you would subtract
So we could then push this way, and which is typically a 151 question, how much excess oxygen do we have? Right? So if we change this a little bit, so given 0.15 moles of hydrogen, 1 mole of oxygen, how much excess reagent do you have? Okay. Well, in that case, I don't care how much product is made. Okay? I just care about which one's limiting in excess. So I could go back to the equation that we set up at the top, 1.5 moles. I generate 0.75 moles of oxygen. I need 0.75 moles of oxygen to react with 1.5 moles of hydrogen. How much mole of oxygen did I have? 1. What's left over? 0.25 moles of oxygen. Okay? Make sense?
That was on the practice, like how much excess of something is left or something there.
I don't remember that.
You told me specifically not to worry about it because we haven't heard it
I'd
yet.
have to look at it. I have to see the question. So we can poke at that in just a second, if you can find it. Someone's got to have the practice exam. We can look for it. Okay. But you get the idea behind the limiting reactant concept? Okay. Okay. So the next kind of fun concept we can add to this is percent yields. Okay. Percent yield. You did trying to think of the experiments you did. The experiment I want to reference for yield, you haven't done yet. It's next week.
No, I think it was the water.
Bugle
hydration,
versus
yeah. That's the closest thing I can think of. We could actually have that in there. I think.
sorta. Let's stick with the bugle versus the nut. Okay, do you guys remember the conclusion of the bugle versus the nut? Which one provided the most energy per gram? Okay, the nut. Okay, when I went through and tested it, I got 500 calories for the bugle, and for the nut, I only got 1 calorie. Shouldn't that mean I should say the bugle should be the answer? Okay, it's not an absolute calorie scale in that case. What are we looking at? It's the calories per gram. When I went through and burned and got 500 calories for the bugle, I burned 500 pounds of bugles. Okay, but I only burned 1 nut. Is that a fair comparison? No. So I need a way to standardize it. So that standardization is taking it back to, well, how much was consumed? The same thing is happening with our percent yields. Okay? If you get a 90 on the next test, are you going to be happy? Yeah? It's out of 200 points. Oh, I didn't say that first. Does that change your perspective?
Yes.
It's not out of 200 points, but I'm just throwing out numbers. Okay? So we have to have something to compare against. It's not an absolute value. It's an absolute value in comparison to a theoretical. Make sense? Okay. So a percent yield will be your experimental value. This is what I got. The theoretical can also be a calculated. The calculated comes from a limiting reagent calculation. Okay? The calculations we just ran assumed the reaction went perfectly. Do reactions go perfectly? No. That's why we can go through and now do a percent yield to decide how perfect our reaction went. Okay? And we could compare to each other. Well, mine was a 90% yield. Yours was a 30% yield. Okay? So I must have done better because I was a 90% yield. Never mind the fact you were only supposed to get 45%. Okay? So we have to have some way to compare and average out those standards. That's the point of a percent yield. Okay? The biggest thing that I want to change on this is this theoretical. We're going to change to calculated. Okay? And it's going to be calculated from a limiting reagent situation. Okay? So those limiting reagent calculations we just did, we'll have to go through and run. right? What are the units on our percent yield? Kind of, and of course I picked a horrible example for it. Our percent yield units need to zero out. Okay? I need to have no units. That means whatever units come from my actual yield, guess what my theoretical yield units should be? The exact same units. As long as they're the same, it doesn't matter what the numbers are necessarily, but I can just compare that calculation out. So someone could go through and do it in moles and someone could do it in grams. And guess what? They'll get the exact same percent yield. Okay? So as long as those units are identical, you're okay. Okay? What units should be used for an actual yield and a theoretical yield? So now not for the whole process, but just an actual, just a theoretical. If you were to measure an actual yield of something in lab, what do you think the units would be?
Grams or
Grams. Why?
you can actually measure it.
You have balances that measure amounts, right? Yeah, that's why. That's how we measure things in lab, is using a balance, which is a mass. Okay? What unit would you expect for a theoretical yield? Grams? Did we use grams for our theoretical yields or our limiting reactant calculations earlier? No, why not? Moles are easier to work with. I don't want to have to go into grams. Well, if I decide not to go into grams with my theoretical yield, what do I have to do with my actual? Convert it into moles. If I don't want to get rid of my grams from my actual, what am I going to do to my theoretical?
Grams.
Convert it into grams. As long as those unit systems are the same, you're okay. Kind of, sort of? Okay, so let's take a look. 2 moles of sodium carbonate are mixed with 2 moles of water and 1 mole of carbon dioxide. And only 0.5 moles of sodium hydrogen carbonate are produced. Then what is the percent yield of sodium hydrogen carbonate? What are you being asked for? The percent yield. How do I calculate a percent yield?
Actual theoretical times 100%.
Am I given either of those numbers?
One of them.
Which one?
The sodium, the actual.
I'm given the actual. Typically, you're given the actual in a lecture class. Why would we give that to you in a lecture class?
We can't do the experiment.
You can't do the experiment. Okay? 0.5 moles of sodium hydrogen carbonate. What do you need to do?
Calculate the theoretical.
You need to calculate the theoretical. I know that says 10%. Give me a sec. How do you calculate that theoretical value?
You use the balanced equation.
Some people may have already noticed that we already did it. Those were the exact numbers of the conversion that we just did for our limiting reactant calculation. And we ran through that limiting reactant calculation. When we started with the 2 moles of sodium carbonate, that led to how many moles of sodium hydrogen carbonate? If I did it right, it was 4 moles of sodium hydrogen carbonate. If we started with our 2 moles of water, what did that end with? 4 moles of our sodium hydrogen carbonate. And if we started with 1 mole of our carbon dioxide, that became 2 moles of our sodium hydrogen carbonate. What was the maximum amount we could make? 2. Okay, I'm going to say that again and see if anybody wants to trip up on that. What was the maximum amount I could make? 2. Isn't 4 larger than 2? Yes, but I ran out of CO2. Okay, so when we phrase it, it sounds like we want to use the largest number. We're still using the smallest number. Moles of sodium hydrogen carbonate. Is that what I have up here? Yeah, so what can I do? I can plug the number in. What happens?
Units cancel.
My units cancel, multiply by 100, and I get a whopping 25% yield. If you can't do the math in your head, that's okay. Was it right? Okay. Don't worry about it. This is why we have calculators. Okay? Make sense?
Where did you put 0.5 moles of sodium hydrogen carbonate in your actual?
Where did I get the 0.5 moles of sodium hydrogen carbonate? If we go back up into the question, there it says 0.5 moles of sodium hydrogen carbonate. Okay? It also says 2 moles of sodium carbonate. I didn't write 2 moles of sodium carbonate. So why was I allowed to write 0.5 moles of sodium hydrogen carbonate? It's not just that it said it there.
It said it's produced.
It says that it was produced. Okay? That English is telling me that's how much I actually obtained at the end of the experiment. Make sense? Okay. Is a 25% yield good? It depends. We don't really know. Okay? Would we want a higher yield?
We don't know that. What's the probably for that?
Do you want a 25% in the class or a 90% in the class? Do you want a higher yield?
Yes.
Yes, you always want a higher yield. You don't want to start something and be like, well, I only got a quarter of the result that I wanted. No, that sucks. That may be all we can get. That's a separate question. Okay? But when we run an experiment, what yield do we want?
100%.
We want the highest possible percentages possible. Okay? We want to be near that 100%. So let's say we ran this experiment and the number we got was 2.5 moles of sodium hydrogen carbonate at the end of the experiment. What is our percent yield? Is it 125%? Okay. 125% yield. Okay. And just to make sure we're clear on this, this is now the new question. We produced 2.5 moles of sodium hydrogen carbonate. What is our percent yield?
Get a new scale.
What is our percent yield? 125%. Guess what most students do?
It's not possible. Write that down.
Put down 100.
They say, oh, 125. I must have done something wrong. It must not be divided by 2. It must be 2.5 moles divided by 4. Guess what answer shows up on the test? That answer also shows up on the test. Okay? Yes, you can get a number larger than 100%. Should you is a different question. Okay? If you're getting higher than 100%, what does that mean? Something screwed up in the experiment. It could be you absolutely cheating. Okay? That's a problem. You should fix that. It could also mean that when you went to weigh it, what did you do with the filter paper? You didn't dry it, and it still got water in it. You aren't accounting for that water mass. Okay, so there are explanations for why you get higher than 100% yield. Just because your number comes in over 100% does not make it a wrong calculation. So don't start fudging numbers because you don't like the number. Okay, this is why you have to trust your methodology. Make sense? Okay. So what could this become? 50.6 grams sample of magnesium hydroxide is reacted with 4.5 or 45, if you wanted to, shift the decimal appropriately, grams of hydrochloric acid. At the end of the reaction, a chemist recorded a dry mass of 60 grams of magnesium chloride. What was the percent yield? We're going to need a chemical equation. Okay? I would argue when we start to try and process through this, we should start at the end. What do I want? How do I calculate a percent yield?
Actual or theoretical yield.
Am I given either of those?
You're given the actual.
We're given the actual, so what am I going to need to find?
Theoretical.
Okay, I need to find this. How do I find it?
Chemical equation.
I won't quite accept that yet. It's a limiting reactant. A limiting reactant would come from a chemical equation. To be able to come up with a chemical equation, what do I have to do? I have to know that magnesium is Mg. I have to know that hydroxide is OH. I have to know that hydroxide's a -1. I have to know that magnesium's a +2. So that is 2. I also have to know that hydrogen's a +1, chloride's a -1, that is balanced. I have to know that when that goes through to react, what happens? I get H2O or HOH, and then magnesium chloride. Magnesium being a +2, chloride a -1. I have to know that that is a 2. Okay? I also have to know that I'm going to need 2 equivalents of HCl to produce 2 waters. Okay? What else do I have to then do? I just did it. 50.6 grams of magnesium hydroxide needs to become
Moles of magnesium hydroxide.
nope. The whole point is this is doing my limiting reactant. I need to find my theoretical. What are the units on my actual? Grams of magnesium chloride. What do I need to convert the grams of magnesium hydroxide into? Grams of magnesium chloride. How do I do that? Okay. Am I going to need the periodic table? Yes. Am I going to need a balanced chemical equation? Yes. Am I going to need the periodic table again? Yes. Okay. But then I can just plug that number in. No. Because then what else do I have to do? This is a limiting reactant calculation. 45.0 grams of hydrochloric acid. What do I need to turn that into? Grams of
magnesium chloride.
magnesium chloride. How do I do that?
Use the periodic table.
Periodic table. Balanced chemical equation. Periodic table again. Okay. Now I can compare those two numbers. Which one do I use? The smaller number. What do I do with it?
Plug in the theoretical.
I plug it into the theoretical. Then what do I do?
Calculate
Actual over theoretical
that.
times by 100%, and I have my answer. Is that a lot to do?
Yes.
Yes. Do you have the ability to do every single one of those steps?
Yes.
Yes. That is how awesome you are and how much you've picked up through the course of the semester. Do it.